Good afternoon, good morning, whenever you're watching the video. Today we'll be discussing a very important chapter in physics called the laws of motion. I will draw this and also it is commonly known as Newton's laws of motion. Sir Isaac Newton had postulated this law, so it's called Newton's laws of motion. So I think it's very it's law. Many of you might have known that Newton's had got three laws of motion: first law, the second law, and the third law of motion. But before we move into the three laws of motion, we would understand the concept from where it is evolved. It has evolved from this thing called force. Force, what is force? We know force is something that can push or pull, right? Push or pull. That's what is our understanding of force. It can change, it can change the direction, it can change direction of a moving body. It can stop or start a body. It can change the speed of a body. It can change the speed of a body. Okay, and these are the few things it can do. So before you understand detailed about how force is affecting the laws of motion, you have to understand a few more things about force. And first of all is, what are the different types of force that's there in nature? What's the different types of forces? So force can be classified into mainly two types. First one is your contact force. So what's a contact force? What's a contact force? A contact force is something that need to be in contact or in touch, that need to be in contact or in touch with the body on which it is acting upon. So the examples, few of the examples of contact force are, we all know this thing called a frictional force. A frictional force, right? A frictional force is a force that acts between two surfaces. If two surfaces are in contact, like you are walking, so your fit is in contact with the ground, and there is a friction between your feet and the ground. That's why you're able to walk. That's why you're not slipping down and you are able to walk. So frictional force is something that's a contact force. If you are but you if you're walking, your hand is not in contact with your uh, ground, so there's no frictional force between your hand and the ground, so it's both the bodies should be in contact. Next type of force that is a contact force is normal or reaction force. We called it a normal, also known as reaction force. So this kind of force acts perpendicularly upwards. For example, if we keep a book on a table, so if this is a table and you have a book on top of it, or a block on top of it, because of the weight of the book, there is a force which is acting downwards, right? But the book is not going inside this table. That's because there is a force which is opposite to it, and it's perpendicular to this table. This is perpendicular to this table, 90 degree. So that's why it's also known as a normal or a reaction force. Reaction. This force is because of the reaction of the force of the book, or the weight of the book acting downwards. That's why it's known as a reaction force. This will also be there when there's a contact between the book and the table. If there is no contact, there is a no normal or reaction force. Third type of force or a contact force is something which is known as a tension force. Tension. Okay. Tension means whenever you stretch a string or a rubber band, there is a force which is trying to pull this rubber band or the spring together or make it smaller. But since you are pulling it like this, so it is not able to do that. So that is known as a tension force. For example, I'll give an example. I have taken a ball, tied it to it with a string, and I am hanging it here. So this is my ball. This yellow color is a ball, and just like your normal force, this ball will also have a weight out here, right? This is the weight of the ball, and because of this weight, the string that we have tied up with this is pulled down, is stretched down. Since it is stretched down, it will form an opposite force on the opposite side, which is denoted by T and is known as a tension force. A tension force. This is known as a tension force. This T is a tension force. Okay, this is also in contact force. The spring or the string on this, in this example, is getting this force because it is in contact with this ball, and the ball is trying to pull it downwards, and the string is trying to pulling it upwards. The force which is pulling the thing upwards is known as the tension force, and the heavier the ball, the heavier the tension, the more the tension force, because these two forces are balanced. This T is equal to W. Okay, so and the string is totally stretched. It is like totally stretched kind of a thing. Okay, right here also you have W out here, and this is the reaction or normal force. We can denote it by R. Right here also R is equal to W. Right, this is balanced. These forces balance each other. Forces, if the force is not balanced in the case of the string or the tension force, the string would have just tear, or it will just break down, right? Okay, this is for the string. Another kind of contact force which is very similar to a tension force is known as the force exerted by a spring, or spring force, or whatever you can call it, in whatever name, does not really matter. It's very similar. It's I'll also put it in the same color so that you know. Spring, force exerted by a spring. We all know spring exerts a force, right? A spring is something, if it is so like this. A spring is something like that. So whenever I am if I'm pulling this string with a force F, the spring itself is trying to go back. Okay, we say that S. Okay, so these two forces are same, right? That's why it's like this. So you use the spring force in lot of things, like in gun, also in bows and arrows. The string acts as a spring action. We stretch this string of the bow, and then when we leave it, the arrow flies off. Or even when we coil a gun and put a bullet and then shot it, because of the spring inside, there's a force coming in. So all these are contact force. So we have got number 1, we have got number 2 as normal or reaction force, we have got number 3 as tension force, and we have got number 4 also as spring force. The last very common contact force is force exerted during collision, like means when two bodies touch each other or hit each other, which is known as, we can say this is collision, force exerted, or we can just term it for how we'll remember is collision. Like when two bodies hit each other, it's called a collision force. When two bodies hit each other, like there is body A, right, and there is body B, right. So somehow if somehow this is moving this side and this is moving this side, and if they hit one another, there will be a force. Each one of them will give a force towards one another. Like if I now make them hit, like it has not become smaller, just so hit each other. So what's going to happen? This is going to hit this side and this is going to hit this side, and then this will go off. This yellow ball was moving this side and it will like fly off the other side, and the red ball was moving this side and it is going to fly off this other side. So this is because of the collision. So this is known as collision force. This is known as collision force. So force during collisions. So this five are the most common contact force. Most common contact force that we see in nature, right? So as I have mentioned, there are two types of force. One of them is this. The other one that we'll be talking out here is a non-contact force. You must have understood by this now. It's a non-contact force, and sometimes a very, very mysterious force. So we can tell this as a let me draw it out here. We can tell this as a non-contact force. This is non-contact force. Non-contact force. So as the name suggests, you must be understanding that means that two bodies on which the force are acting are not in contact but are far off. But how is it possible? We have seen in our daily life that if I'm not touching a ball, I'm not able to move it. It's not magic, right? It cannot just happen just like that. It seems to be a magical phenomena. A non-contact force seems to be a magical phenomena. But believe me, it is not. When I will explain it to you, what's really happening and how is it happening, you'll understand. Okay, this is very common. We know this. One of the most common non-contact force that we all know is force of gravity or gravitational force. Is gravitational force. It's called gravitational force or force of gravity. Right, gravitational force. We know the earth pulls out, like we fall down. We cannot fly off. We have heard of this. The earth has gravity, and because of this gravity, everything it's coming towards the earth. Everything falls down. If you throw a ball up, it will come down. The reason behind what? Because it has gravity. If I just throw a ball up like this, we know that it will eventually come back like this, right? Eventually fall off because of gravity. This is the force by which earth pulls us. Okay. Eventually in your higher class you will know that not only earth pulls us, everything pulls everything, but because earth is such a huge mass or a huge comparison to everything else on earth, that the pull of earth, it's so prominent that other things does not really gets affected, right? So gravitational force is a non-contact force. Even if you are like even if you have thrown the ball up and the ball is high, it's not in contact with the earth, right? It's in the air. It will eventually come down because of this gravitational force. The next type of force that or non-contact force that we should know is called an electrostatic force. Electro, because this force is something, before even studying about this, you have experienced this. Okay. It's the same experience that we get when we take a comb and then comb our hair, dry hair, and bring that comb near to the bits and pieces, right? And then I'll draw this thing so that you can understand. We take this comb, then this is this comb, and we rub it on our hair, and then we have this bits of paper, bits of paper, which gets attracted with this. Is because of some kind of a force, an unseen force which you can't see, and and let me do right. So some kind of attraction happens, and this is because of something called an electrostatic. We would read in details later, right? There are some static electrons that are on the surface of this comb, and that gives a opposite charge to the paper, and that's why they attract. Okay, so that's an electrostatic force. That's an electrostatic force. We call it a electrostatic force. Is also not in contact. We don't have the papers and the comb should be very close together but not in contact, and the paper will get attracted. So that's another non-contact force, right? And third type of non-contact force is a very common force that you have seen since our childhood. Is called a magnetic force. It's called a magnetic force. And magnetic force is something that we during our childhood days have always played with. We have played with a magnet. The magnet is some kind of a black color material, always dark in color, that stick. Right, we have taken magnets and stick it on your refrigerator or your almirah, something like that. So it's a black color thing. Or you brought this magnet and then you got some nails, iron nails, close to that, and you see just iron nail jumps over and get attracted to this magnet, to this thing called a magnet. So that's the magnetic force. This is also the magnet and the nails need not be in contact. It will automatically get in contact, right? So in this leave, you have to note a very important thing about this non-contact force. Is that there is some general character of this non-contact forces. Okay, there is some general characteristic for this non-contact forces. All of it, we have some general characteristics, right? So called general character. Okay, of this non-contact forces that we should have some knowledge about. First and foremost thing, gravitational force. This gravitational force is an attractive force. It can only attract. That means it can only pull. Gravitational force will only pull, or gravity can only pull. It cannot push, can only pull, right? It cannot push. Rest other forces can pull as well as push. Other two non-contact forces like the electrostatic force and the magnetic force will pull as well as push. Other forces like the electrostatic and magnetic force will both pull and push. That means we will see that sometimes magnet will repel others. That means it will repel another magnet. Okay, we'll know that if the two poles are simply repel. So but gravity can only push, it cannot only pull, it cannot push, right? So this is one characteristic of non-contact forces, right? And second is that as we go far away from this uh, bodies, as we go far away from these bodies, the attraction, the force of attraction diminishes. That means the force, especially the non-contact forces, the non-contact one, okay, I'm talking of non-contact, is inversely proportional. It's inversely proportional to distance. To distance. That means we know these two bodies which are not in contact, will experience this non-contact force, right? But if you take a magnet and put the iron nails far off, maybe 10 centimeters or 2 feet far off, you will not see the force. Only if you bring it closer enough, not totally directly attaching to it, but close enough, we would see this force out here, will experience this force out here, right? That means all this non-contact force has a field of force. You will be learning about magnetic field, electrostatic field, and the field of gravity kind of a thing, okay? So earth is not pulling Pluto, because earth and Pluto are far off, but earth is pulling the moon, it's not pulling Jupiter, right? So because Jupiter is too far off, earth's gravitational force is not there, not acting at Jupiter. So as we increase the distance, the force will diminish, right? So actually it is, though it's, I'm rating proportional, inversely proportional distance, actually it is, if we'll see in this chapter only, when we talk about gravity, this force is inversely proportional to 1 by distance square. This is for your non-contact force. This is 1 by distance square. Now we would be discussing about the laws of motion. Now when you've understood force or different types of forces, especially the contact and the non-contact forces, we'll be moving into the laws of motion. We'll start with the first law of motion, which it's a very easy to understand thing. Sir Isaac Newton's first law of motion, or Newton's, will say the first law of motion, right? The first law states that a body, listen to this very carefully, a body will remain in the state, not in solid liquid gas, but remain in the state of motion or of rest if there is no external forces applied on it, right? That means someone who's sitting out, that means if someone was sitting at some place, it will keep sitting at some place, still someone else is putting a force on it, which means a body cannot move itself without an external force applied to it, right? So what we would write in terms of the first law of motion is, we'll write a body body means, when I'm talking of a body, I'm talking something which is a non-living body. The living body can give force internally, right? So you're not able to understand why I was running at thing, I was walking and I started running. There was no force from outside, this is an internal force. When I'm talking about body out here, I'm talking of a non-living body, a non-living object, right? Like a ball, like a toy, like a car, like a phone, like a brick, like a book, like a pen, like a pencil, like a table, right? Where we need an external force. A body will be at rest right? Okay, let me write it in a different manner so that you will remember it properly better, right? I'll say a body could be in two phases, either at rest or it could be in motion, or it could be in motion, right? That means either it is moving or it is not moving, right? That moving is also the, if it's in motion also, it's at a constant, it's a uniform speed, like speed is constant. You can write a constant, you can write a constant speed. Right, when talking of motion, I'm talking of motion at a constant speed. A body will remain in this until and unless, or you can write unless an external force is acted on it. Until an external force is acted on it, which means so this is the first, this is the second. So this is Newton's first law. It's very simple. We can read the definition from the book, but it means a body will be at rest or of motion. That means a body can only move or it is not moving. Is there any other state? No, either it is moving or it is not moving, right? So whichever state it is in, if it is at rest, if it is not moving, if it is sitting somewhere, if it is lying somewhere, it will be there. It will be there unless I put a force on that. So if this is a brick out here, right, or a book out here, it will remain as it is. It will not move unless I am putting an external force. External, that is from outside. Brick के अंदर से आवाज थोड़ी आएगा. So I am putting it from outside. So this is first law. Simply said, this is the first law. But there is if you have to go deep inside this, you will understand what is this first law talking about. The first law is talking about two very important things out here. One is something called inertia. We'll discuss here what is an inertia. And second is talking of force. So first let's discuss what's inertia. Inertia is the property of a body which makes it to stay in the state of rest or of motion. That means any body whose state of rest will remain at rest. Someone who is in state of motion will remain in motion. Question is why? Because of the inertia. Now you might ask, what is this thing called inertia? Is it some magic or something like that? And this inertia gives two things. One is what I've told. One is rest. One is motion. Right. So where is this inertia coming from? Is there anything like density, volume or something inertia is coming from? Some property of a particular body? Yes. Inertia is coming from a very important property which every body possesses, and which is the mass. So inertia comes from mass of a body. Now you see, inertia will make more sense. Now if I say people who has more mass have higher tendency to remain at rest, people who has less mass have lesser tendency to remain at state. So that means if a heavy body is kept out here, something is quite heavy, like big and heavy, maybe 50 kg, and then we take another body which is maybe a smaller one, maybe 5 kg. So if I ask which has more inertia, I don't know, you might think of. But if I ask which require more force, you will very easily say that the heavier body will require more force and the smaller body will require lesser force, or the lighter body will require lesser force. So we agree that a 50 kg body will require much more force than a 5 kg body to make it move, to make it at motion. So we can say the body of 50 kg has higher inertia of rest than a 5 kg body. So this inertia, so the inertia of a 50 kg body is much more than the inertia of a 5 kg body. This is when I'm talking of both the bodies is at rest and I have to start moving. Now imagine this thing. Is it true for inertia of motion also? Let's see. Suppose someone is riding a bicycle, okay, and another person is riding a car, and I need to stop. So which is easy, to stop a bicycle or to stop a car? You can know, like, sir, how will you be able to stop a car? It will just hit me and there will be an accident. For a bicycle, yes, even if you stand in front and you can hold the bicycle, it might stop. So bicycle is lighter, lesser weight, and the car is heavier and more weight, more mass, kind of a thing. So inertia of motion also works the same way. For inertia of motion also, the body with lesser mass have less inertia of motion, and the body with a higher mass has more inertia of motion, kind of a thing, right? For example, think about this thing. If a football is coming towards you and a ping pong ball is coming towards you, we have a football and a ping pong ball. Like, let's say we have a football. Let's draw a football. Maybe this is a football. It's coming towards you. And then we have a small ping pong ball is coming towards you. It's coming like this. It's coming like this. Small ping pong ball with some kind of a velocity, and you might be standing out here wondering what will happen to me. Understanding which is easy to stop or which is easy to hit back? Obviously this smaller ball, it's easy to hit back. The heavier ball is difficult, right? We need more force. You'll be more concerned a football hitting you than a ping pong ball. So here also, this football has more inertia. This has a higher inertia than this, right? This, I write, say football, F. Inertia of this football has more inertia than inertia of this ping pong ball. So inertia is nothing but a property of a body that comes from the mass of a body. Higher the mass, more the inertia. So we can write here is inertia is proportional to the mass of a body. More the mass, more the inertia. So this is one thing this first law is talking about, inertia, right? That is a tendency of a body to be at the position it is in. Now this from this inertia of rest, we will get a few examples that are important both for your chapter and both to understand the laws of motion, right? We'll see what are the consequences of inertia of rest and what are the consequences of inertia of motion. So we would just go through the consequences or some of the examples of inertia of rest. Just remember, these examples are of inertia of rest. These are because of inertia of rest. These are not because of inertia of motion. So how do you remember these are inertia of rest? Let me see how to remember. Let's discuss. Yeah, these are for inertia of rest. This is for rest, or let me draw it. This is for inertia of rest. Let's see first of let's go through the consequences then. When a train suddenly starts moving forward, the passenger standing in the compartment tends to fall backwards, right? You can imagine this passenger was just standing like this, right? And this was maybe the bottom of the train, right? This was maybe the bottom of the train, and when the train suddenly starts, so the bottom starts moving. So the bottom portion of your body will start moving, but the top portion, this portion of the body is still at rest on from your top of your hip joint. So this tends to fall backwards. Actually, this does not fall backwards, since this remains in the same position. This lower portions moved, so we feel that we are falling backward. So how do you know this for rest? Because the entire body was at rest. So what was the initial position? The initial position was at rest, and then it started moving. That means initially it was rest, now it started moving. So understand this. So initially this was at rest, and this is starting moving, right? Second, let's see the second one. When hanging carpet is bitten with a stick, the dust particle starts falling off. The hanging carpet was initially at rest, right? And you started beating with a stick, right? So what happens? The hanging carpet moved, but the dust particles were still there where it was, so it fell off, because there is nothing was holding the dust particles, right? So it fell off. So this is an issue of rest, because initial position was at rest. Whenever you will be given these questions, you have to understand what was the initial position before some action was happened to that particular object or a particular thing or particular situation. In the first case, the train was at rest, then it started moving, right? So everyone at rest initially. So initially it was at rest. So I'm talking of inertia of rest. Let's see the third one. On shaking the branch of a tree, the fruit falls wrong. If you go to a mango tree or something and start shaking it, so what's going to happen? The tree was at rest, so was the fruit, the branches, leaves, everything was at rest. And you started shaking the branches, right? So the fruit wants to be at rest, because that's what inertia is. They wants to stay in the same state until and unless some external force. Here I'm not putting any force on the fruit, but I'm putting an external force on the tree or the branches. So branches start moving, the fruit wants to be in the same position, but when the branches moves, the fruit falls down, right? So that's what this was initially at rest. So this is inertia of rest. So the fourth point is, on striking the coin at the bottom of the carom coins with a striker, the lowest coin moves away, and the rest of the pile will remain intact. So if I try to draw it like this, let's say this was your first, the red one on top, and then we have one white one green one. I'm just putting color so that you understand this, and like this you keep on adding one top of another. We know it's like black, white and red, but I'm just giving color so that. And then you take a striker, which is again maybe red in color, which is again a red in color, and hit the lowest coin like this with a force. What happens? This coin will move off and the others will remain intact. If we do it very fast, you will see this is going to happen. So that's what you have seen, because everything was at rest. You are hitting the lowest coin which is on the board, and it moves, right? So the inertia of rest is applied for the rest of the coins, because you have not given any motion. That's what first law states. And until you give a motion or give a force to a body, it will remain at rest. The other coins remains at rest. So which explains first law of motion and inertia of rest. So this is also an example of inertia of rest, because initially everything was at rest. Let's see let's see point number 5. When a smooth card is placed over the mouth of a tumbler. So let's draw a tumbler. Maybe this is a tumbler. This is a tumbler, and we have put a card on it, like a cardboard card on it, and then we have kept something on top of it. Maybe we have kept some kind of a box on top of it. Now, if you can, with a great force for a thing, pull this thing with a force, what happens is this cardboard will come off and this coin is going to fall inside the tumbler. The coin is not going to move along with that. If you can do it very quickly, it happens. That's because the cardboard has been given a force, which is a pull force, which is great, a force, and it from inertia of rest starts moving because the force is acting on it. That's the first law. But there is no force acting on the this green object on top of it, which could be a small box or something like that. It's still at rest, so it falls directly because it will try to be the same position. It will not go left along with that. This thing will directly fall inside. So it is sitting on the same position because it is still at rest. So this is also a example of inertia of rest, because initially everything was rest. And lastly, the sixth point, when a corridor train means if you move in a first class, you see there are some sliding doors in the first class compartments. So when the train starts moving, if the doors are not locked, it will start sliding the other side, starts moving, because the train moved and the doors are wants to be in the same position, and the train move. Example is very similar to the first point. As the train starts moving, this guy start falling this time. The same here there is a door. Maybe this is the train, and maybe this is the door right out here. This is the door with the knob. So when train starts moving this side, this door out here will try to remain in the same position. So we would see that this is going this side. Actually, it's not going this side. It's trying to remain in the same position that it is in. It's trying to remain in the same position. The train has moved on the right hand side. So relatively, you see it is coming back. So these are all examples of, or all consequences of, or all in nature or daily life, we see all of the things happening. Inertia of rest helps us to explain all this phenomena. So that's inertia of rest. Inertia is because of the mass, more the inertia. Inertia of rest tells that a body will be at rest until and unless a force is acting on it. In all of these cases, there were collection of different bodies, a system of different bodies. In the first case, the train and we as a person are two different bodies connected together because you are touching the train. But since from our hip joint you can move the body, it's flexible, so the lower portion, which is in contact with the foot of the train, or the base of the train, it's moving along the train. The upper portion is still want to be at rest, so it goes back, falls backward. So next we will see some of the consequences of inertia of motion, or some of the happenings in our daily life that could be explained with help of inertia of motion. So now let's discuss this happenings in our daily life that we see around us. You've heard of it, and with inertia of motion, it will help us to explain this. So these are all the phenomena that happens because of inertia of motion. The first one is, a cyclist riding along a level road does not comes to rest immediately after he stops paddling. We all have cycled in our life, or at least taken a ride with a cycle with our parents or uncles, kind of a thing, or still does that. We paddle for some time and we feel like not paddling, like we just stop paddling, and the cycle does not stop immediately. It takes some time, and then slowly it might stop, or we have to brake to stop. Sometimes if you don't have a brake, the brake is the brake has failed or there's some problem with the brake shoes, we'll not able to stop at all. We have to put our legs down and create a friction and use touch the ground to stop it. Sometimes it happens. So why does it happen? This main reason for this is the cycle is an inertia motion. See here, the picture is the cycle is moving. The picture starts, cycle is moving, so everything is in motion. So these will help. Inertia of motion will help to explain this. Initially, the other 6 points we had, like everything was rest and then some force was here. Here, already force is applied and we are at motion at constant velocity kind of a thing, right? No more force is applied. So it will not come to rest because the entire thing is in motion, and we know from inertia of motion from first law of Newton that things that are in motion will tend to be in motion unless there is an external force. So either if you don't brake, it will not stop, or it stops because there is a friction. There is a friction between the tire of the cycle and the ground, and it will eventually stop. It will eventually stop the cycle. But till that, just if you stop paddling, it will not stop. It will take some time, maybe couple of minutes before it stops, and sometimes it does not stop at all, and we have an accident. Okay, right. Let's see the next point. When a passenger jumps out of a moving train, he falls. Why does he fall? Because when the passenger is inside the train, his body is moving at the same speed as that of the train. It's all together one particular system. But then when he jumps out of the train, his entire body still wants to be in the same motion because there's no force has acted on it. But when he hits the ground with his feet, the frictional force between his feet and the ground or the platform has put his lower portion of the body at rest, but the upper portion of the body will still be at motion, and he tends to fall in front on his face. To prevent that, he should run for a few minutes or for a few seconds, so that slowly he can cut down the speed and then stop. A sudden change is always resisted. That's inertia, right? We resist change. Maybe from motion to rest or rest to motion, we resist change. That's the tendency. And the heavier the person, the more the inertia. So a thin person might still survive the fall or have to run a less. But if a fat person has jumped off the running train, he has to run for longer time because mass and inertia related. So for a fatter person or a heavier person or person with more weight or more mass have more inertia of motion, so he has to run a longer time. But the main reason is lower portion of the body has come to rest because it's hit the ground it has zero, ground is not moving, but the upper portion of a body is still at the same velocity of that of the train, and it tends to fall off. So that's the second reason. To the third point, when a running car stops suddenly, the passenger tends to lean forward. This is exactly opposite to what happens when you are sitting in a train at rest and suddenly the train starts moving, so you tend to fall backwards. Here, like the car or something, and the body is totally moving forward. It's moving forward, right? But then whenever it stops, the lower portion of your body has come to rest because it is in contact with the car, but the upper portion is still in motion, exactly same as a second point kind of thing. The upper portion of the body is at motion, so it tends to follow. That's why you should always wear a seat belt. You should always wear a seat belt kind of a thing. This is because of inertia of motion. See, all these points starting off, things are moving, so here the reason is inertia of motion, not of rest. We tend to make some confusion which is inertia of rest, which is inertia of motion. Things that starts with moving things, running things kind of a thing is all of inertia of motion, and the points or the happenings that start with it was now starting, that kind of a thing, like the inertia of rest will be used to explain those things, right? Let's see the fourth point. An athlete often runs before taking a long jump. Now imagine whenever an athlete is jumping, or even you are jumping, you want we want our entire body to fly up in the air and then fall. Now if we just stand and try to jump, whatever, see, our bottom portion of the body is at rest, the top portion is flexible, we can do that. So why an athlete runs? Because to make the entire body in motion, to make its entire body in motion, an athlete first runs for a few seconds, then it's easy for the athlete to take the jump, because now everything is motion, from motion to another motion, from running motion to a jumping motion, both are in motion. So it's inertia of motion right out here, it's not inertia of rest. So it's easy for the athlete to move uh, from inertia of motion to another inertia of motion, both are in motion. See, the moving to jumping to running to jumping kind of a thing. Or else initially just standing to jumping, from inertia of rest to jump, it's difficult. So to make the entire body and give the body an inertia of motion, an athlete first runs and then it jumps, right? So let's come to the fifth point. A ball thrown vertically upwards by a person in a moving train comes back to his hand. See, when the ball is in the hand of the person, and right, so let's see, this is the train, and maybe this is the person standing right out here with a ball in his hand, right? Okay, so now the train is moving, like this. Okay, the train is moving like this, and the ball, the person, the train, everything is in motion. Now he when he just throws the ball upward, like if I say he has thrown the ball upward out here, right, the ball is still in motion, because there is no other force that has acted on the ball. The only force that was acting on the ball was bringing it forward, because the ball in this case, in this picture, the ball, the person and the train are in motion in this side. So this still is moving along with the person and the train, because no force has stopped it. So that's the fun of inertia of motion, right? The ball is still in motion. So as the person is moving from here to here along with the train, the ball, if it has been thrown here, you have thrown in this position, will also travel along with the person to this side, and eventually it will come back to his hand, right? Since the ball is also moving, that's what it is. Even if I've thrown it, it has not come to rest, because there is no force acting on it. The only force is gravitational force that will bring it down. It will not take it this side. No, it will not take it this side. It will only bring it down. So that's why it is coming down. But still, its motion is towards this. Like the person, the ball, and the train are all moving at this forward direction, even when it is thrown upward. That's inertia of motion. This can only be explained by inertia of motion kind of a thing. So that is your entire crux of inertia of rest and motion. So that explains your inertia of rest and motion. Now we would go and move and check the next part of same motion in one dimension. There is another thing that is involved. One is obviously inertia, and another word that is involved in this is force. See, in Newton's first law, there are two things. One was inertia, that body will be at rest. Another thing that is force. So here we'll be talking a bit of force. This is our first law of motion, that force. So let's discuss the role of force. A force is something or to be an external force is something which can move a stationary body or can change the state of motion. That means a force can either move a stationary or body at rest. We'll use the word rest because that is easy for us to understand, or or it can change the state of motion. That means increase or decrease pace. Change, this we have already discussed when you're discussing force. Change the state of motion. It can increase or decrease speed, stop it, or you can write speed, change speed, or speed change. A force can do that. So a force can either move a stationary body or move a body at rest. Right? You can start moving a body at rest, like you have seen in inertia of rest. If you put an external force, you can do that. Or it can change the state of motion. If someone is moving, I can increase the speed or decrease the speed, kind of a thing. That's the role of an external force in first law of motion. So this concludes your first law of motion, and next we would be doing the second law of motion. We will see how much change a force is making. A force can make a change according to first law, but how much change? Does it depends upon something apart from the force? Does it depends upon inertia or mass of a body? That all we will see in our next class. So this has given you a total picture of laws of motion, different types of force, contact and non-contact, different types of contact force, different kinds of non-contact force, even some of the characteristics of non-contact force. Then you went to first law of motion. Then you have discussed about the definition of first law of motion. Then you have discussed about inertia of rest and motion, and different situations in which inertia of rest and motions are applicable, with some of the examples that are important for your exams. Also, we have moved into what is force and what can force do, right? So that will be the first class.